In this section, we're talking about thermodynamic processes. This is when we do work on or by a system, add or remove heat, and or change the internal energy of a system. Usually our system in this case is a gas, but it could be any fluid. We're looking at 4 thermodynamic processes, 4 specialty cases. The first specialty case is isovolumetric. First thing you should know is iso means constant. So constant, in this case isovolumetric, means constant volume. So our volume is constant, but you might hear it said other ways in other places. It's also called isochoric or isometric. Probably the most common out of all these phrases is actually isochoric, but our textbook uses isovolumetric. Kind of like isovolumetric because it's a little easier to figure out. Iso is constant and volumetric makes more sense than choric in this case. So during this process, no work is done on or by the gas, or on or by their system. The reason no work is done is because if there is no change in volume, there is no movement. And in order for work to be done, there are 2 conditions. There must be a force and there must be movement. So no movement, no work. This occurs when the fluid is in a rigid container. So if it's in a rigid container, it cannot be expanded. There could be no expansion or compression on or by the gas. Some examples of this would be the sun heating up a car with its windows rolled up. So heat enters the air inside of the car, but the car's air cannot expand or be compressed because the car is a rigid container. Another example is heating up a fluid in a pressure cooker. Pressure cooker is just a pot with a lid on top that is sealed shut, so the gas cannot escape, nothing can enter. We might have a gauge on top to tell us the pressure. And so it's a rigid container, and therefore it would be isovolumetric. The next type of thermodynamic process is isothermal. Again, iso constant. In this case, thermal like thermometer, temperature. So if it's isothermal, constant temperature, that means that the particles are not moving any faster or any slower. And if the particles move at the same speed, that means that the energy of each particle stays the same. And so the total energy of all the particles stays the same. And so therefore our internal energy stays the same. So during an isothermal process, there is no change in internal energy. This occurs when there are 2 things that could cause this. The first one is that it could occur when there's a gradual expansion or compression. The other times it could occur is during a phase change. Let's look at the phase change first. Anything like melting ice into water, or perhaps boiling water into steam, or freezing water into ice. Those are all isothermal processes because during a phase change, the temperature always stays the same, etc. Now, why is a gradual expansion or compression isothermal? Well, to understand that, let's look at an example. Let's look at a situation where we have a balloon and we add heat to this balloon. You might say, how could you possibly add heat to something and the temperature stays the same? Well, if we graph the temperature versus time, let's say we just add a little bit of heat. Again, we're doing this gradually. We add a little bit of heat so the temperature does increase. But then we back off and we stop adding heat and we let it come back down to room temperature. Now we add heat a little bit again, increase the temperature just a little bit, and then we back off and let it come back to room temperature. We keep doing this over a matter of time, and although the temperature does fluctuate, it does not fluctuate by a whole lot. So the overall trend is that the temperature almost stays the same. Close enough to being an isothermal process that we don't have to worry about a little bit of fluctuation. We call this a quasi-static process, meaning it's almost not moving. It's almost staying the same. An example of this as well would be slowly inflating a bicycle tire, so you'd have to be using something like a hand pump instead of using an air compressor. It has to be done gradually. The next thermodynamic process is adiabatic. So there's no iso, there's nothing staying constant or the same. Instead here we're saying no heat is added or removed. Remember, you don't possess heat. So it's not you can say your heat stays the same. Instead, we're not adding or removing heat to our system. This occurs when there is a rapid expansion or compression. And so if we expand or compress it fast enough, there's not time for heat to enter or to be removed. An example would be inflating a balloon with a helium tank. So what we're doing is, as we inflate that balloon with a helium tank, it's a rapid inflation, a rapid expansion, and so we do push those molecules faster, increasing the temperature a little bit. There's not time for heat to be moving around, moving out of the balloon and then into the air. Another would be a rapid compression of a car's piston. So again, we are pushing the particles faster, and so therefore increasing the temperature in the piston. However, we are not adding or removing any heat. It happens too fast for heat to change from one place to another, to move from one place to another. The very last type of thermodynamic process is isobaric. So again, iso means constant. In this case, baric, like barometer, means pressure. Most situations we encounter will be isobaric because the container is open to the atmosphere during the entire time. Now, one thing we can do here is if it's isobaric, we can calculate the work done. We had said before that pressure is force over area, and therefore force is equal to pressure times area. Now, work is force times distance, and if we replace the force with pressure times area, we get that work is pressure times distance, area times distance. And so if we look at one of our examples here of what we had talked about before, a piston, let's say that we compress this gas inside the piston, and so we move it a certain distance here to a new location. We see here that this volume of gas, this change in volume, is equal to the cross-sectional area of the piston times how far it has been moved. So this volume, change in volume I should say, is equal to the area of the piston times the distance we have moved it. So this here is our change in volume. So the work done is pressure times change in volume. Some examples of isobaric processes would be boiling water in a pot without a lid. So again, it's open to the atmosphere. An ice cube melting in a glass of water. Again, it's open to the atmosphere. So the idea here is that work is pressure times change in volume only if it's an isobaric process. So there are 4 thermodynamic processes. There is isovolumetric, isothermal, adiabatic, and isobaric.